So first one is reflection using Huygens principle of light. Okay, what are the prerequisites for this? You should know that a wavefront, whenever it is moving in one particular direction, the ray of light will be always perpendicular to this wavefront. Let me repeat again. If you have a wavefront, the ray of light is always perpendicular to this wavefront. For example, if I want to draw such wavefronts, let's say here, let me draw it. Let's say this is my plane wavefronts which are emerging out in one particular direction. Then I can draw that the direction in which the light ray is propagating, that will be always perpendicular to these all wavefronts. This is the core concept you will require to understand this whole derivation, this and the next one. So let's see now. Let's draw our reflecting surface. This is your reflecting surface. This is polished from one side so that light cannot enter this medium. And let's say there are two rays. You can think of many rays, but I am taking here two rays. Let's say this is one ray, first one. And let's say this is the second ray, which is traveling and going to the surface. So if these are the two rays, can we draw the wavefronts? Yes. How will we draw the wavefronts? So wavefronts will be perpendicular to these two rays. If they are heading towards this like this, then the wavefront, incident wavefront, that will be perpendicular to these incident rays. So where to draw? You can think of such perpendicular wavefronts, many perpendicular wavefronts like this. Each one of them are 90 degree. All of them you can think of. Many such wavefronts. But which wavefront we have to draw here? We have to draw the wavefront, the last incident wavefront. So here, this is your last incident wavefront. We require it. So which one we will take here? The last incident wavefront, because incident ray is coming and hitting here. So this is the last one, which is very important. And which one we will take for the reflected rays? For reflected rays, we will take the first wavefront. Okay. What is the angle between the rays and this wavefront? 90 degree over here and 90 degree over here. Okay. So just keep in mind these two basic concepts. So let me write here, this is our incident wavefront, the last incident wavefront. And these two brown rays, they are incident rays. Now if I make perpendicular here, if I make perpendicular over here, this is the perpendicular. Perpendicular to whom? Perpendicular to the surface, to this surface. Let me write here, this is my 90 degree over here. What is this angle? This angle is angle of incidence. What is angle of incidence? The angle made by the incident ray with the normal is called as angle of incidence. Okay, great. So, we also know that this angle is 90 degree. Which angle? This red angle is 90 degree. So, what will be this angle? This will be 90 minus I. If that is 90 minus I, then what is, let me make it with the yellow color. This is I. I hope this is clear. Okay, great. Let's now draw our another rays, that is reflected rays. So let's make here our reflected rays as, if this is our I, let's make a reflected ray over here. Let's say this is our reflected ray over here. So this black ray I am making, but black I have already chosen. So let's make this red ray. This red one will be what? This is our reflected ray. Okay, fine. So similarly, I can think of a reflected ray over here also. and if these two are the reflected rays, can we draw our first reflected wavefront? Yes, we can. Where it will be? Make perpendicular to both the red rays. So if I make a perpendicular to both the red rays, it will look like this. 90 degree to both the red rays. You can make it perfect if you want, like this. Yeah, this is better. So this blue one is our what? This is our reflected wavefront. So let me write here. Here. Reflected wavefront. Now, let's use the same analogy. So if I want to make a perpendicular over here, this is the normal to the surface. This is our normal, right? So if this is normal to whom? Normal to the surface. Which surface? The orange one. The orange one, which is our reflecting surface. So what is this angle? This angle is R. If this is R, what will be this angle? Over here, up till here. This will be 90 minus R. Why 90 minus R? Because the blue line and the red line, they are perpendicular. Sir, why they are perpendicular? Because the rays are always perpendicular to the wavefront, and the blue one is the wavefront. And the red one is the reflected ray, and blue is the reflected wavefront. So both will have a 90 degree. So that is 90 minus R. But we know that this complete angle here is 90 degree. So what will be this angle? This will be R. I hope this is clear. Okay. This is your ray diagram. Once you have drawn the ray diagram, everything is done. Now let's name it. Let's take this as M, and let's take it as N. Let's take it as A. Let's take it as E. Let's take it as C. Let's take it as B. Okay. Look at the triangles. Triangle A, E, C. And the triangle ABC. What is angle AEC? Sir, AEC is 90 degree. Why 90 degree? The red one is the reflected ray, and the blue one is the wavefront. So both will have 90 degree. AEC is 90 degree. What is angle ABC? ABC is also 90 degree. So AEC from the first triangle is equal to ABC of the second triangle. Yes. Okay, great. Secondly, AC is common in both. AC is common in both. Now the time taken, listen very carefully, this third one is very important. The time taken for the incident ray, the brown one, the first one, this one, to go from here to A, okay, and from A to E, this point, in the same time, the incident wavefront from B goes to C. So in the same time, we can say that our AE will be equal to BC, and hence these two will be congruent. So triangle AEC is congruent to triangle ABC, and if they are congruent, then we can say this angle I over here must be equal to angle R. By which theorem? CPCT, corresponding parts of a congruent triangle. And if they are equal, then we have proved reflection, laws of reflection, that angle of incidence must be equal to angle of reflection. Let's move to our next one, that is refraction. So let me remove this and let's write here refraction using Huygens principle. Refraction using Huygens principle. Huygens principle. Now let's see. So in case of refraction, we know in this phenomena what happens. The light is entering from one medium to another medium. So let's draw two mediums first. So let's say, let me make it with a box. So, and put some color in this box, and let's put this color as, okay. So this is medium 2. Let me write here medium 2. This is our medium 2. Any medium. And this is our medium 1. Any medium 1. Now what is happening here? Again the same concept. Our rays are going like this. The first one. And this is the second one. These are two incident rays entering this medium. Let's draw the normal for each. So let's say this is our normal for the first point. What is normal? 90 degree to the surface. Which surface? The medium at the point of incidence. This is first one. The second normal is over here. This is 90 degree over here. So what is this? This is angle of incidence over here. We know that. Angle of incidence. And if I make our incident wavefront, how it will look like? Recall. Sir, it should be perpendicular to both the incident rays. So this is our last incident wavefront. Is it making 90 degree to both the brown rays? Yes. So this is our incident wavefront. Let me write here incident wavefront. What is this angle? We already know this from the previous derivation, reflection, using Huygens principle, that this is our angle of incidence I. Okay, great. Now, after doing a refraction at this point, what is this point? This point is point A. This point is C. Moment it enters the medium, it will bend towards the normal. But be very careful. Why very careful? In the first medium, the speed of light is v1. In the second medium, speed of light is v2. Is our v1 equal to v2? No. Is v1 greater than v2? Yes. Is v2 less than v1? Yes. So when it enters, it will bend towards the normal because we are going from rarer to denser medium. Medium 1 is rarer and medium 2 is denser. Secondly, if you call this as our first ray, incident ray, and this is our second incident ray, the first incident ray is going from this point to point A. In the meanwhile, the second one is reaching at this point. Let's call this point as B, at point B. The second one, when it enters from B to C, in the same time, let's say the time taken by this is T. In the same time, this is going from A to this point. Let's call it as E. The distance BC, is it equal to AE? No. Why it is not equal? Because the speed of light is different. Time is same. Time taken for the light ray to go from B to C is same as time taken for the light ray to go from A to E. Okay, great. Can we draw the refracted wavefront now? Yes. So the refracted wavefront will be perpendicular to both. So this is our refracted wavefront. Let's make it perpendicular here. Okay. Okay, great. So if this is I, what will be this? This will be angle of refraction. We already know that. How? Just now we did in the previous derivation. So what will be our BC? BC distance will be speed is equals to distance over time. What is distance equals to? Speed into time. What's the speed in the first one? V1 T. And AE is what? V2 into T. Great. Now, since this is 90 degree, sir, why this is 90 degree? The wavefront is always perpendicular to the rays. And here also it is 90 degree. Let's take the first triangle, ABC. In this triangle ABC, what will be our sine of I using trigonometric identities? Sine I is perpendicular, which is BC, upon hypotenuse, which is AC. Next is triangle AEC, that is sine R, that will be equals to AE perpendicular over hypotenuse, which is AC. And then if I divide this equation 1 with equation 2, what will I get? I will get sine I upon sine R. That will be BC upon AC and AE upon AC. AC cancels, you left with BC upon AE. What is BC? Just now we have done. BC here is V1t. So let's write here sine I upon sine R, that will be equals to V1t over V2t. And T cancel, so we left with V1 upon V2. And V1 upon V2, the ratio of velocities of the light in the two mediums, that's nothing but the refractive index. So hence we have proved that our refractive index mu is sin I over sin R. That is our Snell's law. This was our refraction using Huygens principle. Okay, let's move to the superposition principle now. So the superposition principle, let's start. Let me write here. Before we go to superposition principle, we require coherent sources. What do you mean by coherent sources? Coherent source of light is those sources which produce light waves having same frequency, same wavelength, a constant or no phase difference. Very common question in the board exams. Define coherent sources. So coherent sources are those sources which has same frequency, same wavelength, constant or no phase difference between the two waves. Okay. In your course for 12th standard, we have superposition of two waves with a constant phase difference and with no constant phase difference. Okay. So let me start with the two waves, superposition of two waves with no phase difference. Let me be very careful. Here we are dealing with coherent sources, which means the first wave, let's say it is like this. The second wave will have the same nature like this, same wavelength, same frequency, everything same. So the orange one and the black one, these are the two waves. A wave is represented by a wave function, and this wave function from 11th standard is A cos omega t. Sir, what is A? Amplitude of the wave. Sir, what is omega? Angular frequency. And what is t? Time. What is y? The position of the particle along y-axis at any instant. That is our wave function. So y1 is the first wave. Which one? Let's say orange one. And y2, I am taking it in the black color. So y2 will be for the black one. That is also same. Sir, why there is no different parameters in the two equations? Because both the waves are similar, same. Now you are taking two waves with no phase difference, and these are coherent waves. In coherent waves, every parameter is same. So according to superposition principle, the total wave function or the net wave function of such a wave will be y1 plus y2. We will add. Let me repeat from 11th standard the proper way or proper definition of superposition principle. According to superposition principle, the net wave functions will be equal to the sum of individual wave functions. If you are adding more than 2 or 3 waves, if one person is shouting, if another person is shouting, or if there are 10 people shouting, then the total impact will be the sum of individual impacts in a simple language. So y will be equals to y1 plus y2. y1 is a cos omega t, y2 is a cos omega t, and when you add both, it will become twice of a cos omega t. So from here what we can say, what we found, that if the y1 is the first wave, then its intensity is amplitude square. The intensity of the second one is amplitude square, and I1 equals to I2, so let's call it as I0. I1 is the first intensity, I2 is the second intensity, and both are equal. Let's say it's equal to I0. What is the intensity of the resultant wave? The intensity of the resultant wave will be amplitude square. What's amplitude? 2a. So that will be equals to 4 times a square. And what is a square? I0. So the resultant intensity I prime, let's call it, is equals to 4 times I0. So that's the beauty of superposition principle, that it says that if you take 2 waves with the amplitude A, and if you combine them, then the resultant amplitude of the wave will be double the initial amplitude, like this. The amplitude here will be doubled. Doubled means 2 times. And intensity will become 4 times the initial intensity. Now we will verify it with a more general formula where we will take a constant phase difference. So let me move to the other side and let's write here superposition principle for 2 waves having a constant phase difference between them. So let me write the topic name, superposition principle, superposition principle for 2 light waves, 2 coherent light waves having a constant phase difference between them. Constant phase difference. So let's see here. If we are taking the first wave, y1 is equals to a cos omega t, and second wave I am taking y2 as a cos omega t plus phi. What is phi? The phase difference between the first and the second. And now if you are adding such 2 waves which is having a constant phase difference, then what happens? Let's see. Then the superposition principle says y equal to y1 plus y2. That will be equals to a cos omega t plus a cos omega t plus phi. Let me be very careful here. We can't add them directly because one is cos omega t and another is cos omega t plus phi. So cos A plus cos B, you can't add them directly. You will have to use an identity. So let's write it as A cos omega t plus cos omega t plus phi. Now let's take the identity here, cos A plus cos B, and that will be equals to twice of cos A, this is from 11th standard, A plus B by 2, cos of A minus B by 2. And this we can write here as A 2 times cos omega t plus phi whole divided by 2, and cos omega t minus omega t plus phi by 2. Let me repeat again. A is nothing but omega t, this one, and B is nothing but omega t plus phi, which is this one, and I have placed it in the above identity. So let's take that 2 outside. So 2a cos omega t plus omega t, twice of omega t plus phi whole divided by 2, and cos omega t minus phi whole divided by 2. Now cos is an even function. Remember that from maths. So cos minus theta is cos theta. So 2a cos phi by 2 I am writing in front. And the second parameter I am writing here as cos omega t plus phi by 2. Now this parameter, the one which is written in the black, that parameter is having a time dependency. So that is, if you compare it with our actual wave equation, that is a cos omega t, if you compare it, then the red part is called the amplitude of the wave. So what is this 2a cos phi by 2? That's the amplitude of the resultant wave. Sir, why do we trust you? Because if there is no phase difference, if we go back to our initial derivation, if there is no phase difference, in that case, this is first case, for no phase difference, what we have solved in the first case, phi will be equal to 0 in that case, and y will be what? 2a cos 0 upon 2 cos omega t plus phi by 2. What is cos 0? Cos 0 is 1. So that will be 2a cos omega t plus phi by 2. Now, what's phi here? I didn't substitute here phi. Phi is 0. So 0 divided by 2 is 0. So let's remove this part, and here we left with this. So this is 0. So 2a cos omega t, which is verified over here. Now, this is first case. Second case is very important, and this is called our what? This is called our constructive interference. We will talk about interference in the next lecture. Constructive interference. Next is our destructive interference, and second case is destructive. Destructive interference. Now, what's the condition for destructive interference? A crest is falling on the trough, or the trough is falling on the crest, or in terms of phase difference, phi is pi or 180 degree. So if I put 180 degree in our resultant equation, y will be equals to 2a cos 180 over 2 cos omega t plus 180 over 2. Now what is 180 over 2? 90 degree. And what's cos 90? 0. 0. If it is 0, then multiplied with the whole equation, the resultant at that point is 0. So waves will cancel each other at those points. So in case of constructive interference, waves are combining together and resultant is maximized. There it is minimized. Now what is the intensity of such a wave? Intensity of such a wave will be 2a cos phi by 2, that is the amplitude, whole square. So often in the board exams they ask you to figure out the resultant intensity of such a wave. So 4a square cos square phi by 2.